Get started in a minute or so. Give everybody a chance to get in. And we should be off to experiment. We should be off to chapter 8, which should be acid and bases. And again, if you have questions, feel free to use the chat box. And again, make sure if you could leave the video off so I don't have too many boxes on my screen. I appreciate it. All right, so we'll get started then. So we're off to chapter 8, which is acid and bases. Again, this is going to be the first chapter that will be on, should be exam 3. So remember exam 2, which obviously will be online, chapters 6, 7, and I believe 5 there. And yeah, I would tell you what's on those chapters, but I'm trying to remember. But I think perhaps we got some gases and we got some reactions, and then we have some solutions, if I'm not mistaken, whatever was in those chapters. Exam 2, as we talked about last time as well, I think is going to be moved from, I think it's scheduled for next week. It's going to be moved, I think, to the following week. And again, we'll do it online, and you'll have some more information about that as we get closer. Again, exam 3 will be chapter 8. We're not doing chapter 9, which is nuclear chemistry. And then I think it's 10, 11, 12, and 13. And these are all pretty much chapters that go together. These are all the organic chapters. So I guess the good news is chapter 8 here is pretty much the last calculation chapter. So this is the last chapter that will involve calculations. Pretty much once you get to chapters 10, 11, 12, and 13, which is organic, you pretty much don't need your calculator for anything. There's really no calculations involved. It's more sort of memorization and that type of stuff. But chapter 8 does have a good number of calculations, but after that, obviously, you won't need your calculator too much. So let's get into chapter 8. So talking about acids, acids essentially have a sour taste. They cause litmus paper, for example, to change color. So litmus paper, again, is a little piece of paper, a little strip of paper. And you could either dunk it in your solution or put a little bit of your solution on there. And if it goes from, usually it'll probably start as blue litmus paper, and then it will turn red, and red basically will mean that it's acidic. So it also can react with metals through a reaction that we talked about there, which is a single replacement reaction. So for example, if we take hydrochloric acid and some zinc, the zinc will come in and it will kick out the hydrogen. It will produce hydrogen gas, which is bubbles that you typically see. And then the zinc and the chlorine will come together to make zinc chloride. And do a little balancing there, I suppose. And typically will produce a lot of gases as a result of this single replacement reaction. And aqueous solutions of acids conduct electricity. So acids can be electrolytes. And just like when we talked about electrolytes, acids can be either strong electrolytes or they may be weak electrolytes. And again, we'll kind of remind ourselves what that is as we go through this chapter. But essentially, strong acids will break apart into ions and produce a lot of ions in solution, and thus it will be able to be a strong electrolyte and conduct electricity really well. On the other hand, we have bases. Bases basically have a bitter taste. They do feel slippery. So a lot of soaps, drain cleaner, Drano, those type of things, those are essentially bases. Um, they also change litmus paper. So if you take some litmus paper, and usually if you're kind of testing for a base, you would actually start with red litmus paper. And when you dunk your solution on it or dip it in your solution, it will typically turn blue, and that means basic. So if you use litmus paper like you would do typically in a lab, if it turns red, that litmus paper, or remains red if you dip it in there, but usually you go blue to red, that's acidic. And if you go from red to blue, that means that it's basic. A lot of there are some strong bases that are also very good conductors of electricity, and there are also strong electrolytes as well. There's also some bases that are weak electrolytes as well. And again, we'll remind ourselves when we get there, but this is basically your same definition. If it's a strong electrolyte, then 100% break apart. If it's a weak electrolyte, then it will mainly stay together in solution. So looking at an acid is basically a substance that has the ability to produce H plus or hydrogen ions in solution. So in terms of acid-base sort of chemistry, when we talk about acids, oftentimes we'll see this H plus, which is the hydrogen ion. And H plus in acid-base chemistry is also sometimes referred to as a proton. And it's referred to as a proton for the basic idea of, if you remember, hydrogen is the one element that does not have all three of the subatomic particles. They have a proton. So hydrogen has a proton, it has an electron, it does not have a neutron. So no neutron for a hydrogen atom, which means in order for something to become positively charged, it would have to lose an electron, which means since it doesn't have a neutron to begin with, and when it becomes positively charged, it loses an electron. That essentially just leaves it a proton, which is why sometimes H plus is referred to as a proton because of that. In addition, we will see two sort of formulas for H plus, or the hydrogen ion, that is also interchangeable when we do acid-base chemistry. So when we do acid-base chemistry, we will see the H plus ion, which is our hydrogen ion. We will also see H3O plus, which we'll see in a couple of slides down the road. This is what is known as the hydronium ion. And for all intents purposes in acid-base chemistry, they are basically the same. And what I mean by that is, and depending on where you're looking, maybe a certain book or a formula, you will see H plus used and H3O plus used interchangeable, both in formulas and also in chemical equations and reactions that are written. And we'll talk a little bit in a second why you get H3O plus versus if you just get H plus, but you will see those two things interchangeably used. I personally, most of the time in this chapter, will use H plus. So wherever I use H plus, you essentially can substitute H3O plus in its place. And again, that's the same in formulas and also equations usually. So if we do have a strong acid is a strong electrolyte. So if you remember what a strong electrolyte was when we talked about in that chapter, is in solution, 100% of it will break apart into ions. And if you remember, it is those presence of the ions that make sort of the circuit complete and a very good conductor of electricity. So when we have a strong acid, that means when we have these guys in solution, we no longer have any of the whole units together. So for example, if we looked at HCl, which is hydrochloric acid, and again, you typically will see this aqueous symbol written that also indicates that it is an acid. And usually acids will have that aqueous symbol. Aqueous, again, means basically it's a solution. So that also helps us distinguish between HCl, that's hydrochloric acid, and something like HCl with the gas symbol next to it, which is hydrogen chloride gas. So typically when you write formulas for acids or see formulas for acids, if they don't in words say, hey, this is an acid, you typically will see that aqueous symbol next to it to indicate that it is an acid. And if we have something like hydrochloric acid, which is the HCl on the bottom, in solution, what's going to happen is pretty much it's a one-way street, and you're just going to break apart into H plus ions and Cl minus ions. And again, because it's a strong acid, it's a strong electrolyte. So 100% of what you have in solution is basically those ions that are floating around free. And the basic definition, as we see above, is that an acid is something that has the ability to produce H plus. And basically what this is able to do is, in solution, produce a lot of free H plus. And that's the key there. It's able to produce a lot of free H plus very quickly. And because it's able to produce a lot of free H plus, it's considered a strong acid. You know, you have none of the HCl units still together in this case. It is just that free H plus that's floating around. Any questions on that? So HCl, which is hydrochloric acid, is a strong acid. There's some other ones up there that are also considered strong acids. So the example that's written on the screen is nitric acid, which is HNO3. That's nitric acid. Again, in solution, nitric acid will 100% break apart into H plus and NO3 minus. And again, it's considered a strong acid because it has the ability to produce a lot of free H plus very quickly. And that's sort of your basic definition there of an acid. So there are some strong acids, as we'll see. And I think there's a list that we'll see in another slide, but HCl is definitely a strong acid. HNO3, like we have up there, is a strong acid. H2SO4 is sulfuric acid. HClO4, that's perchloric acid. HBr is hydrobromic acid, that's a strong acid. And HI is hydroiodic acid, that is also a strong acid. So those are like 6 sort of common strong acids that we come across a lot in chemistry: hydrochloric acid, HNO3, nitric acid, H2SO4, sulfuric acid, HClO4, perchloric acid, and HBr, hydrobromic acid, and HI, hydroiodic acid. All of those acids will essentially 100% break apart into ions when it's in solution. Sulfuric acid is slightly different because it has 2 H's, but we don't get too much into that. But for the most part, all those guys will 100% in solution produce free H plus, which is the key for something to be an acid. Any questions on that there? So that way. Now, bases, on the other hand, are substances that are able to produce hydroxide ions in solution. And hydroxide is OH minus, is one of those polyatomic ions. And a lot of strong bases have actually OH minus in the actual formula. So a couple of examples of some strong bases are down here. Let me try it with the pen going the right way. There we go. Sodium hydroxide, potassium hydroxide. They actually have the OH minus in the solution to begin with, and in the actual formula to begin with, and that usually will make them a strong base. So like what we see on the bottom, something like sodium hydroxide will break apart into sodium ions and hydroxide ions like what we have on the bottom there. And again, much like our strong acid, 100% of what you got in that solution are these ions. And because it produces a lot of free OH minus, is considered a strong base in that case. When you look at group 1 and group 2 on your periodic tables, group 1 is our alkali metals. Group 2 is our alkaline earth metals. And pretty much alkaline, the definition of alkaline is basic. Yeah, so that's basically what alkaline means. Basically, it means basic. Yeah. So when somebody says it's alkaline, it means that the solution is basic. And if you think about what's in those first two groups on the periodic table, you have things like sodium, like you have there, that makes sodium hydroxide. You have potassium, that makes potassium hydroxide, calcium hydroxide, barium hydroxide. So a lot of really strong bases come from group 1 and 2 on the periodic table. Now, not all bases has to actually have hydroxide in it. There are some bases that do not have hydroxide in it. But they are still considered bases because they can produce hydroxide. And an example of that, for example, is NH3, which is ammonia. Again, ammonia, not ammonium. So this is ammonia. And ammonia, when it's in water, will produce NH4 plus, which is ammonium, and it will produce hydroxide. And because it's able to produce hydroxide, it is still considered a base because it's able to do that, even though it does not have OH in the actual formula. When it's able to react with water, it's able to produce hydroxide and is still considered a base. You may also notice something that we've seen before as well when we look at the actual arrows that I drew here in this reaction. These arrows here are reversible arrows, which means there's a forward direction and a reverse direction. And usually we see that when we talk about something that is a weak electrolyte, which means in solution, you mainly have, this guy still together, but it's able to produce a little bit of hydroxide. So it's still considered a base, but ammonia would not be a strong base. It's actually considered a weak base because of that. Any questions on that? So a lot of really strong bases come from group 1 and 2 on the periodic table, and they actually have hydroxide in the formula. There are a number of weak bases. Ammonia is a very popular sort of weak base that, although they don't have OH in the actual formula itself, they're able to react with something like water and produce OH minus, which still makes it a base, but it's a weak base. Any questions on that there? Yeah. So what happens when we do take a strong acid and a strong base together? And if we take something like HCl, which is hydrochloric acid, plus sodium hydroxide, which is sodium hydroxide, which is a strong base. Again, as we talked about, this is really a double displacement type reaction. The H from the acid and the OH from the base is going to come together, and that is how we get our water. So these guys are going to produce our water, And then we will also produce, when the sodium comes together with the chloride, sodium chloride, and this is what is referred to as a salt. So remember, in an acid-base neutralization reaction, these are the two guys that are always formed. You always make water, and typically in a strong acid, strong base situation, the H plus comes from the acid, the OH minus comes from the base, and again, they come together to make water. So that's where the water comes from. And then obviously the salt comes from the other part of the acid and base when it comes together. If we actually look at a reaction of a strong acid and a strong base, when they do come together, no matter what combination of strong acid or strong base that you put together, the ultimate reaction that is actually taking place is really just that: the H plus from the acid and the OH minus from the base are essentially coming together to make water. So that is really the reaction that is truly taking place when you mix a strong acid and strong base together. And that's why it's called, again, an acid-base neutralization reaction, because essentially one thing that you're making is water. So going through sort of what's truly happening in that reaction is what we see here. And we don't have to worry too much about it, but ultimately the reaction that we get is this guy here. It's basically the formation of water. And really the formation of water is what is sometimes referred to as a driving force for a chemical reaction to take place. So there's really three sort of things that occur that are kind of driving forces for reactions to take place. And a lot of them we talked about when we did the chapter about different types of reactions and ways to classify reactions. One such driving force is basically an electron transfer. That's what occurs when we do some type of redox reaction, which is our oxidation and reduction reactions. The formation of a solid, which is a precipitation reaction, is another sort of driving force for a chemical reaction. And the third driving force is the formation of water, like we see here. So that's a very big sort of force. The H plus has an extremely high attraction to OH minus. So when those two guys get near each other, they oftentimes want to make water, and they will want to come together. We don't really talk about these other types of reactions up here, so we don't have to worry about it. But this is what is sometimes referred to as the total ionic equation. And basically what it represents is when we have all these guys in solutions, these ions are basically in that solution floating around freely. And that's what's going to allow our H plus and our OH minus to come together to make our water. And really in that solution, we still would have the sodium and the chlorine, basically just kind of chloride floating around freely. Any questions on that? Here's again a couple other examples as we talked about before in a previous chapter. That is typically what you get there is basically water and a salt that's formed. And again, a salt is just a fancy word. I'm not sure how fancy that is, but it's a fancy word really just for an ionic compound. And remember, an ionic compound is a positive and negative guy that's together. So our sodium is positive, our chloride is negative, our potassium is positive, and our nitrate is negative in the next one here. So these guys over here are our salts. Yeah. And obviously these guys are water. So when we do write these reactions, again, no matter what combination you put together, that is what you would expect to occur, which is a salt and water. So if we take something like HBr, which is hydrobromic acid, again, positive, negative, plus our potassium hydroxide, which is our strong base, positive, negative. Again, the positive H plus and the OH minus is what's going to come together to make our water. And then we're basically left with a K plus, and on this side, we're left with a Br minus. So these two guys would come together to form our other guy, which would be KBr. And again, we would have formed our salt and our water over here. Any questions on that reaction? Again, an acid-base neutralization reaction is essentially a double displacement reaction that is going on. Any questions on anything? Again, if you do have questions, feel free to type it in the box. I will see it as I shuffle everything around. There's some boxes. So let's talk about sort of some early definitions of acid and bases. So sort of the first early sort of definitions of acid and bases was one that was made by Arrhenius. And he basically said that an acid is something that has the ability to produce H plus ions in solution. And again, our H plus ions is really, I'll be honest with you, that is how you can recognize something as an acid. Yeah. So if you see H plus floating around in the solution, H plus is somewhere in the formula, it's probably going to be something to do with an acid. Just like over here, the sort of basic definition of a base is something that's able to produce hydroxides in solution. So again, as we talked about a little bit earlier there, something can produce H plus in solution, and something can produce hydroxide in solution as a base, but not all bases, again, like NH3, for example, need to have hydroxide in the actual formula. So for example here, if we dissolve those guys, that's essentially how we get something like hydrochloric acid, and that really is the distinction between hydrochloric acid and hydrogen gas, for example. So it actually starts as a gas, but then when you kind of bubble it through water, it will break apart into these ions, and then now you have that strong acid that's formed, which is known as hydrochloric acid. And again, a very strong acid because in solution, you have a lot of those free floating H pluses. Same thing if you take some solid, some sodium hydroxide, when it dissolves, and it will dissolve in water, it will produce a lot of those hydroxide, and again, making it a strong base in that case. So it was a really good sort of step forward in terms of acid-base chemistry. It was kind of limited in terms of the idea of the type of base that we could talk about. And a lot of the types of bases that he dealt with were these strong electrolytes that actually had hydroxide in the formula. And this was good until pretty much the next sort of definition of acid and bases was sort of a more generic definition of acid and bases. And this is one, as we'll see in a second, which is known as the Brønsted-Lowry definition of an acid and base. And Brønsted-Lowry sort of came up with a definition of an acid and base that is a little bit more generic, if you will, a little bit different of a way of applying the ideas of acid and bases. And it is oftentimes the concept that most people think about when we talk about acid and bases. So usually a lot of times we think about sort of acid and bases in the Brønsted-Lowry definition. And basically Brønsted-Lowry said that an acid is a proton donor. So it is something that gives away an H, but important as well is not just the H, but also the plus goes along with it. So as that acid donates that H plus, charges will change because of the plus part of it. And they said that a base is essentially a proton acceptor. And that again means that something will gain not just the H, but it will also gain the plus with it, which will affect the charge. So when we talk about something, for example, like HCl, which is a strong acid, as we talked about in the last sort of slide, in solution, it will break apart 100% into our H plus and Cl minus. And this is a perfectly okay way, perfectly fine way to write this strong acid, break it apart into its ions. And when we write it like this, what we end up with is our H plus. Now, you could kind of write this same reaction. It's not really a reaction. It's really sort of what's happening when we put hydrochloric acid sort of in water or when it's in solution. And we could write the same sort of way as sort of a Brønsted-Lowry definition where we take our hydrochloric acid and we add it to water. And what happens is, since this is an acid, by the definition, it's going to donate its H plus over to water. And when it donates its H plus over to water, the water gains a hydrogen. So it goes from H2O to H3O as it gained that hydrogen. And again, the important part here is not just the hydrogen, but the plus as well. So it goes from something with no charge to a +1 charge. And then what's left is, since the water in this case would be acting as our base and it would be accepting it. So what's left here for our acid is just Cl minus. Yeah. And this way of writing how this strong acid dissociates is sometimes referred to or ionizes. It's probably spelled really bad. I apologize. But this is also a very perfectly fine way to represent how an acid like this would be breaking apart in solution. Now, this also brings up what we were talking about kind of on the first slide, that in acid-base chemistry, H plus and H3O plus are essentially the same thing. And you can see when we include water in the equation for an acid like this that's going to dissolve, that is when we see the formation of H3O plus, or the hydronium ion. When we sort of don't include water, which is very common in the equation when we write a reaction for a strong acid, that is when we get the H plus that is formed. They're again identical to each other. Both of these reactions are perfectly fine ways to demonstrate how hydrochloric acid is breaking apart in water. But again, some people will write it without the water, and some people will write it with the water. And the main thing is, if you write it with the water, that's pretty much when you're going to produce that H3O plus. If you don't write it with the water, you will produce the H plus. So that is why when we talk about sort of acid-base chemistry, the H plus and the H3O plus is essentially the same thing. And again, you can write it either way. Not one way or the other is wrong per se. Again, I personally, just out of practice, especially with acids, really we'll write it like what we see up here on top. But your book and other places may show the exact same thing written like this with the water. So typically if you have the water, you'll really have this Brønsted-Lowry definition, and that's usually when you'll produce that H3O plus. But again, for acids, you can oftentimes leave the water out of it and write the equation just like it is on top. Any questions on that, and sort of how come H plus and H3O plus are the same? It's really for that reason there. I will say that for bases, most people will include the water and write it like a Brønsted-Lowry sort of reaction. So they'll include the water reacting with the base, much like what I did on, for example, we'll go back there. Okay. I was talking about those bases. Right there. For example, oh, that was far back. There it is. So, for example, when somebody writes something for a base, especially a weak base, they oftentimes will include the water, usually most of the time in the reaction, like I did there. And again, this is also really a Brønsted-Lowry definition. In this case, the NH3, as we saw earlier, is a base. Water in this case is actually acting as an acid. And what's going to really happen in this reaction is the water is actually going to donate the H plus over. And again, it's going to act as an acid. The NH3 in this case will actually act as a base and accept it. So if you look at NH3, it goes from NH3 to NH4, gains the extra hydrogen, and then also the plus. And when water loses H plus, you can think of water and acid-base chemistry as like H and OH. So when it loses that H plus, what is left is OH minus that's left over, and that's what we see over here. So when people write sort of reactions that involve bases, a lot of times, if they're not strong bases, but a lot of times with weak bases, they definitely will include the water in the reaction. Any questions on that while I scroll back through where we're at? All right. So when we do have a reaction that's written sort of as a Brønsted-Lowry reaction, it actually creates partners that develop. And over here, HA is an acid. So HA is just a generic sort of formula for an acid. So for example, HA could be HCl, HBr, etc., where A is basically the negative guy and the positive guy is H plus. Yeah, they come together. So if this is an acid, in this case, our water is going to act as a base. So what's going to happen again is our acid is going to donate the H plus over. When the acid donates the H plus over, it is left as just A minus on this side. And when the base accepts the H plus, just like we saw before, it will become H3O plus. And what this creates are two guys, one on each side, that are related to each other. So the HA here is related to the A minus. And if this is the acid on one side, its partner on the other side is what is known as the conjugate base. So the partner is the conjugate base. And on the opposite side here, grab a different color. Our base on this side is related to a guy on this side. And if it's the base on the left-hand side, its partner on the other side is what is known as the conjugate acid. So we get these acid-base conjugate pairs. And if you look at sort of the difference between the acid on one side and the conjugate base on the other, the difference between this acid over here and our conjugate base over here is a difference of 1 less H plus. So the difference between the acid on the left and the conjugate base on the right is just 1 H plus difference. If we look at the base and its partner on their side, which is the conjugate acid, the difference is also 1 H plus, but it's 1 more H plus. And that H plus that we're talking about is right here. It is that H plus that is being transferred from the acid to the base. And that's an important relationship to remember. In order for something to be an acid conjugate base pair, or the opposite would be a base conjugate acid pair, the only difference that can be there between those two things is 1H plus. So it has to be only a difference of 1H plus. And by the way, when you look at a reaction, your regular acid and bases are always on the left-hand side of the arrow. And on the right-hand side of the arrow is where you find your conjugate acid and base, conjugate base. So your conjugate guys always on the right-hand side of the arrow. The product side, your just regular old plain acid and bases always found on the left-hand side. And the only difference that there can be between those two things is just 1H plus. It cannot be more than 1H plus. It cannot be H plus and some other element difference. The only difference has to be that H plus. Any questions on that? Okay. And here again is the example where we looked at hydrochloric acid and water. In this case here, our hydrochloric acid is obviously acting as an acid. Water, again, in this case, is acting as a base. So our acid is donating the H plus over there to our base, which is water. Again, when the water accepts the H plus, it makes H trio plus. And when the HCl loses the H plus, it becomes Cl minus. So when HCl again loses the H plus, it becomes Cl. And again, it has no charge here. But when you lose a positive, you become more negative. And that's where the negative comes from. So again, the charge does change as things either lose or gain that H plus, which is an important thing. And again, the only difference, as we can see, between our HCl and our Cl minus is just 1H plus. Any questions on that? All right, so let's take a look at some, I think. This is just the Lewis structures of what's happening here. And again, I'll leave it up here, but we essentially kind of covered it. Again, HCl going to be donating that H plus. And when it does, it makes H0 plus, which is really a polyatomic ion. It's got a bunch of nonmetals together there with a charge. And again, acid-base chemistry, this and H plus the same. Yeah. All right. So I'll give you a second here. You want to try to decide which one of these, or which ones of these, I guess, are a conjugate acid-base pair. So take a look through each of those and decide, are those two things related to each other enough to become a acid conjugate base pair? Then we'll talk about it in about a minute or so. Okay, so let's take a look. So when we're trying to decide whether or not these are acid conjugate base pairs, really it is that right there. It is the H plus that we're looking for. And again, remember that the difference has to be only one of those. Yeah. So when we look at HClO4 and ClO4 minus, what we're looking for is, are these things related to each other? And if they are, is the only difference as we go from one to the next 1H plus? And if you look at it, the answer is yes. So you could look at it one way. You could take off the H here and the plus, and you'll end up with the ClO4 on this side. Or you could put the H plus on and you'll end up with the HClO4. So this one is an acid conjugate base pair. When we look at number 2, HCl and ClO minus, again, we want to look at the two and decide whether or not, or what the difference is. Is the difference an H plus? The difference between those two things is, yes, it is an H plus. So you might be inclined to say it is an acid base pair, but there's also another difference. The difference is a O. And remember, the only difference that there can be is just an H plus. So these two are not related to each other because one has an oxygen and the other one does not. Any questions on that one? When we look at the next one, which is H2PO4 minus and HPO4 2 minus, we're looking for, again, that difference of an H plus. So the answer is yes, there is a difference of an H plus. And again, if you take the H off of here, you'll be left with HPO4. And as we go from -1, when we lose the H plus, -1 becomes -2. So this is an acid base conjugate base pair. And lastly, when we look at these two here, the difference here is also, yes, just one H plus. And again, you can look at it however you want to look at it. You could take the NO3 minus, and if you add an H plus to it, you put the H on it, you get an NO3 plus 1 and -1 equals 0. And we do get HNO3, which is over here as well. So this would be a pair. So it looks like the only one that is not is number 2 is not a pair. Any questions on how we determined that there? Okay, so again, the important thing is only one H plus difference in order for something to be a pair. So let's take a look at some of these here. We are looking for the conjugate base for each of the following. So I'll give you a shot there. Why don't you take a look and see what you come up with for the conjugate base for this guy. All right, so when we look at this one, what we want to look for is the conjugate base. So the first thing that you should know, hopefully from this, is the difference should be an H plus. The key thing here is, should you put it on the H plus or should you take an H plus off? And that's really the hard part for a lot of people. So the way you could kind of think about this is what we've been talking about, sort of the relationship between an acid, a base, and its conjugate acid and base pair. If you remember, the acid is related to the conjugate base, and the difference is one less H plus, while the relationship between the base and the conjugate acid is one more H plus. So in this particular problem, we're asked to write the conjugate base. So we're asked to actually write this guy, the conjugate base, which means what we are looking at is way back over here. We are looking at an acid. So we could consider this an acid because we're being asked to solve for the conjugate base. So you could kind of think about it backwards to determine, should you put it on or should you take off the H plus? And the way you can do that is your basic Brønsted-Lowry definition of an acid is a proton donor, which means if this guy is an acid, we should actually take off the H plus. While if we were doing the opposite there and we started with a base, we should put on the H plus as it's a proton acceptor. Any questions on that? So sometimes in these problems, they ask you just to write the conjugate acid or they ask you to write the conjugate base. And the easy way to sort of think about it is just to think backwards and think about what you are looking at. And in this case here, as we just determined, we are looking at an acid, which means it should take off the H plus. So we basically want to write it with one less H plus, which would give us HS. Again, here it has no charge to begin with, but when it loses that H plus, the plus part will turn this into a minus. So this is HS minus would be the conjugate base for that guy there, H2S. Any questions on that? So using that same logic here, if we're still looking for the conjugate base, again, this is going to be an acid, which again means we want to remove an H plus. So we want to take it off. And again, when we take off the H plus here, we're left with just sulfur. And here we are starting with -1. So when we lose that plus, it goes from -1 and becomes one more negative. And that gets us 2 minus would be our answer here, S2 minus. Any question on those first two? Continuing on with this thought process, again, this being an acid means just like the other ones, we're going to remove an H plus, and that's going to leave us one nitrogen and two hydrogens. Again, here it does not have a charge, but when we remove the plus, it's going to become negatively charged. So again, when you lose the plus, it becomes more negative. And I think we might have one more here. Now the last one here, same idea. Since we're still looking for the conjugate acid, the conjugate base, we're going to take off an H. So when we take off an H, we have just one H left. We have an S and an O and a 3 in that case. And what that means is, in addition, because of the plus there, we are also going to make it a minus. Yeah. And that would be its conjugate base. Any questions on any of those four, or how to write a conjugate acid or conjugate base if you're given something? So let me give you one here and you give it a shot. Let's go with HCO3 minus. That's HCO3. And why don't you write the conjugate base for it? And while you're at it, why don't you write the conjugate acid for it as well? So we're looking for two separate answers, one where this is the conjugate acid and one where it would be the conjugate base, both starting with HCO3 minus, which is bicarbonate. So why don't you take a moment here and give that a go? And again, if you have questions, feel free to ask. All right, let's see how we're doing. We'll start here with the conjugate acid part. So using, again, our same logic, in the first part here, we want to figure out the conjugate acid, which again means that it had to start out as a base in this case. So as we're going over here to figure out the conjugate acid, that means we're thinking of this as a base. And again, the definition of a base is something that will accept an H plus. So in this case, we would actually put the H plus on. And when we do, we end up with two hydrogens, a carbon, an oxygen that has three, and then +1 and -1 gives you no charge here. So we would end up with H2CO3, which is known as carbonic acid, and that would be the conjugate acid in this case. Any questions on that one? Now, if we take the same thing and we're going to start with the HCO3 and we're looking for the conjugate base, so much like what we did in this problem, the conjugate base means that we started out as an acid in this case. And the definition of an acid, much like what we did in this problem, means that it's going to donate an H plus. So in the case to going to the right here, the HCO3 minus is actually acting as an acid and it's going to donate it, which means we will end up with one carbon, three oxygens. And now when we lose that plus, we go from -1 to -2, which is carbonate. So this example here is a good sort of example. This is something that can act as both an acid and a base, and something that has the ability to act as both an acid or a base is what's known as amphoteric. It's an amphoteric substance. Is a substance that has the ability to act either as an acid or a base. And a lot of times when you get something that has a hydrogen in it and a charge, those are usually the guys that can act either as an acid or base, as we'll see. And as we sort of saw already, Water as well is amphoteric. It can act as an acid or a base. It could be an acid in certain situations. It could be a base in others. Any questions on acid conjugate base pairs? And really the reason why we say it is just an H plus one at a time is when something like, say, sulfuric acid, which is H2SO4, when it loses a hydrogen, it actually loses it one hydrogen at a time. So for example, the first thing that would happen is it would lose one hydrogen and become HSO4 minus. And then the next step would be the HSO4 minus would lose another hydrogen and become SO4 2 minus. By the way, as you might imagine, it is much easier to do this step than to do this step. So most of the hydrogen that comes off will come off with that first hydrogen that comes off. The second one, not a lot of it will come off, but most of it will come off of the first one. But this is why when we talk about something like H2SO4 and something like SO4 2 minus, these two guys are not partners, are pairs. Yeah? Because the difference here is more than one H plus. And the reason for that is pretty much what I just wrote up there on top. The H pluses come off one at a time, which means that this guy and this guy here, these guys are partners. The difference is one H plus. This guy and this guy are also partners, as the difference is just one H plus. But if you try to jump straight from here to here, they're technically not partners because the difference is more than one H plus. And that's why you need something in the middle like HSO4 minus, which is a partner to this guy, and also a partner to this guy. And as you can imagine, this guy right here is also amphoteric. If it gains a H plus, it will come this way, which means it acts as a base. If it loses an H plus, it will come this way, and it means it acts as an acid. So also has the ability to be amphoteric. It could act as an acid or a base. Any questions between the relationship between an acid, a base, a conjugate acid, or a conjugate base? So obviously you need to be able to identify those things. And much like this example here, you need to be able to write either the conjugate acid or the conjugate base, obviously if the acid or base is provided for you. Any questions on any of those steps there? Okay. So when we talk about acid strength, we talked a little bit about sort of strong acids and strong bases. When an acid is in water, it will produce H3O plus and A minus, and that's your acid base reaction that we saw earlier. Some of those guys can recombine, and this would be an example, again, that reversible reaction, which tells us it's weak, like a weak electrolyte. So something like hydrofluoric acid is a weak acid. When it breaks apart, it does break apart into H plus and F minus. And again, a reminder that what we got going on here is a weak acid, which means in solution, this is mainly what you got going on. You have a little bit of these guys, but it's still considered an acid because it has the ability to still produce H plus. So since it's able to still produce H plus, it's still considered an acid, but it's a much weaker acid than something like hydrochloric acid, which essentially just needs to go for a swim. and is going to produce all H pluses, a lot of free H pluses. So it's a much stronger acid over here as opposed to this, which would be a weak acid. Another very common weak acid is acetic acid, HCO, I'll say it right, we'll try again. CH3COOH is one way acetic acid is written. Sometimes it's written C2H4O2. These are acetic acid. That's basically your acid and vinegar. And it's also a weak acid. So when it's in solution, what you mainly have is this guy still together, but it still will break apart into H plus and acetate. But you have just a little of these guys. And again, mainly you have this. So a way you could recognize sort of a weak acid, much like you could recognize a weak electrolyte, as I really butchered these arrows here, is those arrows that head again in both directions, which implies that it's a reversible reaction, much like what we saw when we looked at electrolytes. Any questions on that? So this we sort of talked about as well. So again, this is basically what we're talking about. If the forward reaction predominates, maybe not with as giant of an arrow there, it's basically going to be a one-way street like your hydrochloric acid. 100% of it is basically heading to the right, and you got H plus and Cl minus. And obviously, if sort of the reverse reaction predominates, that means that you have basically a weak acid like the ones we just saw on the previous page, like hydrofluoric acid, even though it is producing a little bit of those ions, the H plus and the F minus in this case. This again is mainly what you got in that solution, and pretty much the equilibrium is kind of going in this direction here, and it's basically keeping that together, but still producing a little bit of those H pluses, which allows it to be an acid still, because by definition, still able to produce H plus. Again, nowhere near the amount of H plus that would be produced in something that's like hydrochloric acid. So sort of the relationship of between acids and its conjugate base pairs are bases and their conjugate acid pairs is basically an opposite relationship. So if an acid, and then on the other side of the arrow is conjugate base, if it is a strong acid, its conjugate base will be relatively weak, which means it won't go on and react further. And vice versa, if the acid is a weak acid, its partner on the other side will be strong. And sort of outside the scope of this class, what that essentially means is that conjugate base is able to continue to react. And typically, because it's able to continue to react, it will be able to produce more hydroxide and will affect really the pH of that solution and make it either basic or acidic. It really will make it basic in that case because it has the ability to continue to react. Again, we don't really get into that in this class, so you don't have to worry about it. But when we look at the base and this conjugate acid relationship, the same relationship is there. If we start with a strong base, its partner is relatively weak. And if we start with a weak base on the left-hand side, its conjugate acid partner will be relatively strong as well. So that is sort of the relationship that we see between acids and their conjugate bases, or bases and their conjugate acids in terms of strength and weakness. Here are some of those strong acids we talked about. Again, we added, I think, HBr to that, which is hydrobromic acid, hydroiodic acid, also a strong acid. Again, all these guys essentially are going to 100% break apart. Maybe not so much that one, but we'll consider it that. But it will pretty much 100% break apart into those ions. When we think about acids, another way they're sometimes described, HCl, because it has the ability to drop off one hydrogen, or H plus, is sometimes referred to as being monoprotic. Mono meaning one, protic meaning proton, and it's able to donate one proton. Something like H2SO4, which is also sulfuric acid. It has the ability to actually get rid of both hydrogens, as we saw in the previous slide. Again, they do come off one at a time, but because they are able to both come off, they are sometimes what is referred to as a diprotic acid. Again, di meaning two, protic meaning proton. And there's also, for example, something like phosphoric acid. So phosphoric acid is H3PO4. And H3PO4 has actually 3 H's that it can donate. And when it donates, again, just like H2SO4, these will come off one at a time. And if you do the overall reaction, you'll end up with something that looks like this. But again, will come off one at a time. But because it's able to donate 3 H pluses, is sometimes referred to as being triprotic. Again, able to donate those 3 H pluses. Also, sometimes people will use the word polyprotic. Polyprotic just means it has more than one H plus basically to give. Any questions on that there? So as we talked about, water is amphoteric. Water can basically react with itself. It also can act as either an acid or a base. And we saw both of these examples earlier. So in this case, water is acting as an acid. So in this case, the water is going to donate the H plus over. And again, as we saw earlier, it makes NH4 plus and OH minus. This is also a reversible reaction. That's what these arrows mean. Those arrows heading in both directions. And in this case, water is actually acting as the base, which means it's going to accept the H plus and also make the guys that we saw before. Now, in certain cases, and what happens when you do have water in a beaker or whatever it may be, it can react with itself. So we'll just call this guy the acid, just randomly picking. This guy is the base. Again, this guy would then donate its H plus over and we'll make H3O plus and OH minus. And that's what we think about in terms of sort of the strongest acid and bases you could have in solution is H3O plus and OH minus. Is sort of the generic way to represent an acid and a base in a solution. Questions on that? When water does react with itself, the other place that we sort of saw these arrows that head in both directions is when we talked about equilibrium. And if you remember, when we talked about equilibrium, there is a big K, which is known as the equilibrium constant. And at some point, the rate of that forward reaction, like we talked about, will equal the rate of the reverse reaction when you have these reversal ones. And that is what is meant when we talk about something coming to chemical equilibrium, is as fast as it goes to the product side, it is just as fast coming back to the reactant side. And what that does is, for water, creates an equilibrium. And it creates an important relationship when we talk about acids and bases. And that is this relationship right here. It is Kw. And Kw is the equilibrium constant for water. And basically, Kw is something that you should know. Kw equals the concentration of H plus. So again, here I'm going to use H plus, but you can use H3O plus. It's exactly the same, times the concentration of OH minus. And at 25 degrees, which is most of the cases when you do problems, it equals 1 times 10 to the minus 14. So this relationship here is really important. It is how we can determine whether or not, when we have a solution, is it acidic Is it basic or is it neutral? And when we see those little brackets, those brackets mean concentration. Very smallly written. And what concentration typically we're talking about is molarity, moles per liter. So again, when you see those brackets, it implies that we're talking about a molarity. And a very important relationship that we have between H plus and OH minus is as one goes up, so as the concentration of H plus goes up, the concentration of OH minus will go down. So they're inversely related to each other. One goes up, one goes down, and vice versa. Obviously, if the H plus concentration goes down, the OH minus concentration will go up. So a couple of things, we can use this sort of guy as a formula, and we could use this as a formula basically to calculate either the H plus concentration or the OH minus. And essentially the H plus concentration, you could think of it as sort of the acidic part. The OH minus concentration, you could think of it as the basic part. And you can compare both of those numbers together and determine whether or not the solution is acidic, basic, or neutral. And the way you could do that is you could use this guy as a formula. So we could use this guy as a formula, which we'll see on the next page. And you can rearrange that KW equation like we see here. So it is really the same calculation no matter which one you're doing. If you have the OH minus concentration and you want to figure out the H plus concentration, you take 1 times 10 to the minus 14 and divide it by the OH minus concentration, and vice versa. If you have the OH minus concentration and want the, if you have the OH plus concentration and you want the OH minus concentration, you take 1 times 10 to the minus 14 and divide it by that. And you could compare those. So really, if your H plus concentration, which is your acid part, is bigger than your OH minus concentration, then the solution would be acidic. If your OH minus, which is the base part of the solution, is larger than your H plus concentration, then it will be basic. And if they actually equal each other, like they down here, they both will have a concentration of 1 times 10 to the minus 7, which means you would have a neutral solution. So you can calculate these guys if you know either the H plus concentration or the OH minus concentration, and you can compare the two and be able to determine if it's acidic, basic, or neutral. Couple of things, most importantly, our favorite button on our calculator, our exponent button, yes. Hopefully you remember where yours is. You didn't lose it, sell it, whatever you did. Hopefully not. But you want to definitely make sure in this chapter, when you do things in scientific notation, make sure that you are using your exponent button. If you are not using your exponent button when you do these calculations, you are going to see yourself off. Like the front part of the number will be okay, but the exponent part will definitely be wrong. So for example, let's just do one to finish up here, just kind of see how it works. If we have an H plus concentration of 2.5 times 10 to the minus 8 molar, we want to know what is the OH minus concentration, and is it acidic, basic, or neutral? So why don't you take a moment and give that calculation, and we'll see how we do. I will do it as well because I just made it up. So take it together. Okay, so let's take a look and see how we're doing. So first off, you always have this equation, and that is a constant, that number, that 1 times 10 to the minus 14. So you always have that number available to you if you ever need to do any of these calculations, say like in the textbook or whatever you may come across, and they just give you the H plus concentration or the OH minus concentration. Again, a reminder that in your book and other places, they may write it with H3O plus and OH minus equals 1 times 10 to the minus 14, which is our KW. Again, exactly the same thing. So like I said, I typically use H plus, but I know some books and stuff will use H3O plus. So anywhere in any of these formulas that we'll talk about from this point forward, again, you could substitute H plus for H3O plus. So since we're looking for the OH minus concentration, we would want to rearrange the equation just like this. It is essentially the same calculation regardless of which one you're given. You're always going to take 1 times 10 to the minus 14 and divide it by whatever concentration they gave you. So in this case, our OH minus would equal 1 times 10 to the minus 14 divided by the H plus concentration that was given to us, 2.5 times 10 to the minus 8. Now, when we put these in, a reminder about scientific notation, you would want to put in, I'm just going to write on the bottom because I got a little bit of space, I think. You would want to go, you want to hit 1, you want to hit your exponent button. Again, usually we'll put that E, or it may go like times 10 when you do it. And that that is the times 10 part of the number. So we would want to use, again, our negative button, not our subtract button, and 14. We then would want to do our divide button and put our other number in the exact same way, 2.5, our exponent button, and our negative button, which again could look like what I wrote first, or you may have a button that looks like that, and 8. Remember also, if you do have one of those newer calculators that does have a button that looks like this, you got to put parentheses around all the numbers. So remember that as well. And if you put all that into your calculator, you will get a number, hopefully. And that number is, in scientific notation, you will get something like 4.0 times 10 to the minus 7. And since this is a concentration, it would have units of molarity, just like the first one did. Remember that if your calculator is not set to scientific notation, you will get something like this spit out to you. And again, you could write it like that, but sometimes it's better to go scientific notation on this because you will end up with a lot of zeros on a lot of these numbers. First off, any question on the calculation part or how to punch it in, again, make sure you are using your exponent button. But now that we have the actual concentration of the OH minus, this is essentially the base part. We were given the acid part, which is over here. To determine whether or not this is acidic, basic, or neutral, we want to compare those two numbers and see which one is larger. I'll give you a second to think about it. Which one is larger here? So we have the H plus concentration, and we have the OH minus concentration. Which one is larger? They're definitely not equal to each other because they're not the same number, right? So to give you the answer here, the answer is the hydroxide is actually larger, and that's because of the exponent here. This is -7, which means if you wrote it out, it looks like this. This one is actually to the -8, which means if you wrote it out, I'm going to give it the old try here. 1, 2, 3, 4, 5, 6, 7, 2, 5. This one, as you can see, has more zeros, which makes it a smaller number. So when you have a negative exponent, versus times 10 to the negative 7. The smaller negative exponent is actually the larger number. Sometimes people have a hard time with that. Again, you could kind of figure it out if you just kind of write out all the zeros and stuff like that. So this is a very good way to figure out whether or not something is acidic, basic, or neutral. If you're given the H plus concentration or the OH minus concentration, which is typically something that you are given in a problem, you could calculate the other one. Again, basically the same calculation, regardless of which one you're given. You're just going to take 1 times 10 to the minus 14 and divide it by the concentration that you're given. Most people struggle with two things. Most people struggle with inputting it, again, with the scientific notation and your exponent button. And secondly, most people struggle with the comparison of the two when you compare the OH minus to the H plus and that negative exponent. A reminder as well that when you're asked a question like that, is the solution acidic, basic, or neutral? The answer is just one of those. You cannot have an acidic and basic solution at the same time. So again, in all these questions in this chapter, if you're asked, is it acidic, basic, or neutral? It's just one answer. Any questions on that? So I think that's where we will stop for today in terms of lecture. A reminder, I think on the schedule, next week is the exam. I am going to move it to the, I think, following week, if I'm not mistaken, in terms of when it is. And it, again, will be happening online through Canvas. And again, you'll get more information, obviously, as we get closer. Let's see here. Wednesday discussion. Again, we'll take maybe a 10-minute break or so. Let me stand up for the first time today, I think, and kind of stretch. And I'll be back to answer any questions that you may have. If I'm not going to see you there in discussion, have a nice weekend and all that good stuff. And again, I haven't got a chance yet to update the grades or anything like that. So my goal is to kind of do that over the weekend, along with all my other grading. And so I'll try to get you an update, hopefully before next week. Any questions on anything before we call it a night here for lecture? Okay, and again, discussion will begin in probably about 10 minutes or so, and I'll start that second meeting, which, as I mentioned before, everybody's welcome if you want to come in or stop in. Okay, if there's no questions, I will wrap it up here for lecture. Have a good night if you're out, and still have a good night if I'm going to see you in a bit.